Hello everyone, welcome to my channel. In this video, I would like to start working on applications of differential calculus. I have two questions that I want to look at. If you are new to this channel, please do not forget to subscribe. Now, like I said, we are going to look at applications of differential calculus. Our first question of the two that we have in this video, given a string of length p, prove that a rectangle of maximum area that can be formed using this string is in fact a square. So how do we tackle this question? Remember, we are looking at applications of differential calculus. Here is how we tackle it. So we are told a rectangle has length p. So our question one, we sketch a rectangle. That would be a very nice place to start from. We sketch a rectangle. And let's say that the length of this rectangle is, let's say, x, and the width, let's say, y. We are told that the length, a string of length p, is what we're given. So it means if I add from here all the way back to there, the answer must be equal to p. Now we're going to say, therefore, p is equal to, starting from there, x plus, here is y plus, this distance is also x, remember, opposite sides of a parallelogram or a rectangle are equal in length, and then plus y again. Remember, that would be x, that would be y, and that would be x, and that would be y again. So this is what we have. Now let's simplify this. Like terms together, we have 2x plus 2y, and that's our p. Remember, very critical for us to understand and remember that p is a constant, because we're told we're given a string of length p. So p is a constant. Now, if I want to make y subunit formula in this one, I'm going to have to divide by 2 throughout. Term-wise division coming up again. So we're going to say here, this implies that p over 2, it will be equal to, divide by 2 here, you get x, divide by 2 there, you get y. Make y subunit formula, you're going to get y is equal to, subtract x from both sides, y will be equal to p over 2 minus x. Let's call this equation number 1. Now, the question also talks about maximum area. It says, given a string of length p, prove that a rectangle of maximum area. Okay, so we're going to let area be equal to capital A. And we know area of a rectangle is length times width. So we're going to say, therefore, our A is going to be equal to, what is our length? X. What is our width? Y. But remember, we are told, let's call this equation number 2. We are told, at least from here, we can see that y equals p over 2 minus x. So I'm going to have to substitute this expression into that equation there. I'm going to say, therefore, A is equal to x, open brackets. What is y? Y is p over 2 minus x. Now, let's go to page 2. We expand this expression here. Let me just say that from here to there, we are subbing or substituting 1 into 2 to get this one. Substitute that into the place of y to get this. Taking us to page 2, what are we saying now? Let me move down a bit. Right. So basically we are saying that therefore our A is going to be equal to p over 2 x minus x squared. When you multiply x by p over 2, it's going to be p over 2x. Multiply x by minus x, you get minus x squared. We are told we must prove that a rectangle of maximum area that can be formed from a string of length p is in fact a square. All right, so what do we do next? We're going to differentiate, because remember, this is an optimization question. Basically, applications of differential calculus, and this specifically, if you want to look at a concept on its own, this specific question is actually on optimization. So we're going to have to differentiate this. So therefore, dA dx, this will be equal to, remember, this is a constant, p over 2 If p is a constant, p over 2 is also a constant. So we keep that constant and differentiate x with respect to x. The answer is 1. So we're going to have p over 2 times 1 minus, differentiate minus 2 minus x squared with respect to x, you're going to get 2x. And this must be equal to 0 at maximum area, at max area. At maximum area, that's what you should have. Now, let's simplify this equation. So we're going to have p over 2 minus 2x is equal to 0. Let's multiply throughout by 2. Multiply this by 2, you're going to get p. Multiply this by 2, you're going to get 4x. And the answer is, multiply by 2, 0 by 2, you're going to get 0. And what is p equal to? P equals 4x. Now, this is our very serious result here. P equals 4x. So now, I'm going to move back to equation number 1. There is our equation number 1. And we're told y equals p over 2 minus x. So, equation number 1, what does it say? If you want, you can call this equation number 3, because we already have number 2. Equation number 1 says y is equal to p over 2 minus x. So we're going to take this expression and put it in that place there. Again, now we're substituting 3 into 1. This means that y must be equal to 4x over 2 minus x. Now moving on, what is 4x over 2? The answer is 2x. What is 2x minus x? The answer is x. What are we saying? We are saying y equals x. Now let's go back to the diagram. If we move back to the diagram here, if y is equal to x, this can only be a square, because in a square, that's where you have each interior angle 90 and the sides of equal length. And therefore, we can conclude here, our conclusion is, therefore, if we name this one as A, B, C, D, we're going to say, therefore, A, B, C, D is a square. We're going to say here, remember where we're coming from? This is our conclusion. Y equals x, and we're saying y equals x, those two are equal. It means that we have a square here. And therefore, we can say, therefore, AB is equal to BC is equal to DC is equal to AD. What am I talking about? I'm talking about this shape here. AB equals BC equals CD equals DA or AD. And the conclusion is, therefore, we have a square here. Therefore, ABCD is in fact a square. That's how you prove it. Remember where we're coming from? We're coming from the fact that the string given is of length p, and therefore the p is a constant. So we sketch a rectangle, and then we say, but we're told that this string here, out of which this rectangle is made, has length p. So we add that, and that equate to p, and then make one of the unknown subject formula, and then go to area. The question talks about area as well. Here it says, prove that a rectangle of maximum area that can be formed using this string is in fact a square. So we are interested in area as well. That's why we moved to area equals, of course, area of a rectangle is length times width. So we have it there. But we know the value of y. Take this, substitute in here, simplify the equation as follows. And because of the word maximum, shall I say, we have to differentiate this expression, differentiate a with respect to x. Remember, a equals this one here. So we differentiate that with respect to x, and we have this expression which simplifies to p equals 4x. And going back to equation 1, substituting there, we actually find out that x is equal to y. And if a rectangle has equal sides, that rectangle can only be a square. So this is the end of example number 1 in this video. Let's move on to example number 2. Example number 2 we have is this one here. Example number 2, it says, prove that the longest chord of a circle is its diameter. Prove that the longest chord of a circle is its diameter. So now again, naturally we have to start from sketching a circle. So if we sketch a circle, there is our sketch of a circle. And let's have a chord here. This is our chord. We must have a center, and we know that from the center, this distance here is going to be radius of the circle. That distance there is also going to be radius of circle. Let's say it forms an angle of theta between them, right? So I'm going to have this distance here. Let me call this distance from A to B, for example, and our center O. If I call this distance A to B L for length, then we can, by using cosine rule, what do we have? We have L squared will be equal to the square of that distance there, which is R squared, plus the square of that distance there, which is R squared, minus the product of these two times 2, so 2R times R times cosine of the angle opposite our length L, which is our theta. Now we are having now L squared equals, simplify this part, it will be 2R squared, and then we have 2R squared cosine of theta. Now if we at this stage let L squared be equal to, shall we say, let's say W, then we can say that W is going to be equal to 2R squared minus 2R squared cos of theta. Now remember, the question is saying prove that the longest, you see that word there coming up again, optimization, longest, maximum, smallest, least, minimum. Whenever you see those words, differentiation must come in. So here we're going to say, therefore, dw, the theta. Remember, the angle that's changing, what is changing is theta, not so much this distance here and that distance. These are constant, but the angle here, theta, is changing. Let's just put a restriction here. For you to have a chord, theta must be an angle between 2 pi, which is 360 degrees, and it must be greater than 0. So this is the restriction we have on theta. It's the restriction we have on theta. For you to have that length, that angle must be bigger than 0, and it must be less than 360. Otherwise, you're not going to have that line there, AB. Convince yourself that that is true. So now theta is changing from anywhere from 0 but not equal to 0, all the way up to but not equal to 2 pi, which is 360. So therefore, theta is our variable. Now differentiating that is a constant 0, and this part here, remember that is a constant, the first part, minus 2R squared is a constant. Derivative of cosine is minus sine. So this will be minus 2R squared, which is a constant, times minus sine of theta. And this must be equal to 0 at, remember it says longest, at longest length, longest W. Let's just say W is a chord, longest length of W. That's basically what I'm trying to say here. So we solve this equation then. How do we do it? Let's go to page number 5. Solving this equation, hope you can see what I'm writing here. You can. So now what we're saying is solving that equation there, we're having now, remember, minus times minus is positive. So we now have 2R squared sine of theta. The answer equals 0. Divide by 2R squared on both sides. Remember, R is not equal to 0. So we're having sine of theta is equal to 0. Now, we can come up with a general solution for this. Working with radians, we're going to say, therefore, either theta is actually equal to sine inverse of 0 plus k times 360, which is 2 pi radians, right? Or, so let's simplify, let's solve this first. So theta equals, this will be 0, and then you just have 2 pi times k. That will be our first equation. The second equation, remember, we said either, so we're going to have or here. Theta is going to be equal to 180 minus this, and 180 is pi radians, minus sine inverse of 0 plus k times 2 pi. Simplifying this, it gives us pi radians plus k times 2 pi radians, or k times 2 pi. Up there I said, yeah, 2 pi times k, or k times 2 pi, it's the same thing. So this is our equation number 2. Now notice something. If you look at this equation here, we can't get a solution there because of our restriction on theta. if you take, remember k is an integer. Let me just write it. K is an integer here, and k is an integer. Now, if you look at integers, negative integers cannot work because theta cannot be negative. 0 will not work because the restriction here says theta must be greater than 0. So k equals 1, it will be 2 pi. It will not work because theta must be less than 2 pi. So this one here doesn't give us any solution. But if you look at this one here, if you let k equal to 0, it will give us theta equals pi. So k equals 0 in this equation number 2. In number 2, if we let k equal 0, what we get is theta is going to be equal to pi radians. Now, let's go back to our relationship. In other words, the expression for length. This is the expression for the square of our chord, the length of our chord AB. All right, so I'm going back to this part here, which is a simplified form. All right, so, and I'm going to substitute pi radians in there and see what L would turn out to be. So, substitute theta equals pi into our L squared, which is equal to 2r squared minus 2r squared cosine of theta. What do we get? When you sub that, we get, if you like, we get L squared is equal to 2r squared minus 2r squared, and then cosine of pi radians. Now notice something. Cosine of pi radians is actually minus 1. So we're saying L squared here equals 2r squared minus 2r squared, and then times minus 1. Now let's go to page number 6 to just simplify this off, and that will be the end of our calculation. So let's go to page number 6. This is page 6 here. And what are we saying? We're saying we're simplifying this expression. Let me move this up like that. Right. Yeah, it's clear there. So we are basically saying that L squared will be equal to 2r squared. Remember, minus 1 times this number here, minus 1 times minus 2r squared, it will be plus 2r squared. So what is L squared? L squared equals 4r squared. And let's take square root. Remember, we're dealing with positive quantities here. So it is okay for us to say the square root of L squared equals the square root of 4r. And what is L on the left? Remember, this cancels that, and there 4r squared, not just 4r. There's 4r squared there. Our answer is 2r. And what is 2r? This is just our diameter, because we understand that diameter is twice radius. If you go back here, diameter is going to be that distance there, and that will be r, and that will be r, and therefore our diameter, if you call ABCD, our diameter CD is actually 2r. We proved here that that is the longest value of L you can get. You can't get any shorter, any longer value of L than that through our differentiation here and equating to 0. All right, I am going to stop here in this video. I obviously will come back with more questions on applications of differential calculus. We're going to be looking at applications of derivatives, and as well as applications of integration in the case of area and volumes of revolution. All right, like I said at the beginning, if you're new to this channel, support us by subscribing. We truly value your feedback and support. It gives us the ability and the energy to generate many more videos and support as many students as possible. All right, see you next time.